All right, it's my pleasure to introduce this week's speaker, Leander Stecker from University of Leipzig, who will speak to us today about reducible holonomy and closed torsion geometries. So please, Leander.
Thanks, Jeff. So I'm going to talk about reducible holonomy and closed torsion geometries. So it's my pleasure to be here. Thanks for Jeff and Bea for organizing this wonderful seminar. Um, so kind of my approach is I'm going through this concept of reducible holonomy, and I want to arrive at closed torsion, but I'm going to start where kind of most of these holonomy stories start, that is the classical Riemannian case. So, well, suppose I have any kind of Riemannian manifold together with a affine connection. I can look at the holonomy group. And for me, I'm usually only interested in the restricted holonomy group, so I don't care about topology or anything like that. And then we have the holonomy principle, which basically tells you if you have some kind of tensor that is preserved, well, then the holonomy should be in the stabilizer of that tensor. So kind of we want to have we want to restrict the holonomy, so we wanted to preserve lots of geometry. And that's usually the sign of a good connection if it preserves many of the geometric features we have on a manifold. The typical example, Levi-Civita connection, preserves the metric, so its holonomy is in a special orthogonal group. And well, then the classic question people ask, and back in the 50s, what are the possible holonomies if they're like a strict subgroup of this special orthogonal group? And there are two theorems, and you probably all know these theorems very, very well. So the first one was by de Rham, and well, if the holonomy representation splits, then the two factors are basically the tangent spaces of two submanifold or two manifolds, and our manifold is a product manifold, at least locally. So we can go to the universal cover and then it's global. And once you have kind of this, well, you can reduce the dimension and split off all the factors, and then you at some point are left with only irreducible factors. And at that point, Berger's theorem, probably the most classic theorem, tells us that, well, if we have a irreducible holonomy representation, then there's only a handful of possibilities. So namely, except for the generic case, we have these Kähler, Calabi-Yau, quaternionic Kähler, hyperkähler, parallel G2 and parallel spin 7 cases, and that's essentially all. I mean, there it is, symmetric spaces, but well, they're special in their own right. But basically, we have a very restricted set of possible holonomies. And that is the classic story in the Riemannian case and Levi-Civita case. And then you look at this list, and then you notice, well, its advantage is it's such a short list. Like all of these geometries are super special, super nice, and they are well studied, like for that reason. But that's also the disadvantage of this list. It's kind of short. It's maybe too short in the sense of what about odd geometries? Geometries in odd dimension that is not 7. 7 would be G2, but apart from that, none of the odd geometries appear here in this list. So you may want to extend kind of your scope where you're looking at. And how do we do that? Well, that's the question I just asked. So the thing is, I want to keep my Riemannian metric preserved, so there's only one way. I have to add torsion. So for me, the torsion is generally contracted with the metric to a 3-0 tensor. It's by default skew symmetric in the first two entries, and then we have this third entry. And now you can decompose it in the sense of orthogonal representations. And if you've been here last week for a talk, then you've seen that happen already. So there's one representation of the orthogonal group in there, that is the purely skew symmetric case. So when all three entries are skew symmetric, and that's what we call skew torsion. So why should we care about that kind of torsion? So my argument is they are very close to the Levi-Civita connection in the sense that if you have a connection with skew torsion, you get them in the following way. You take the Levi-Civita connection and you just add the torsion 3 form on top of it. And the advantage of this thing is, well, if you have if you're looking at geodesics of this new connection, then they are basically the geodesics of the Levi-Civita connection because the torsion term just doesn't matter in this case. So they preserve lots of geometric features of our Levi-Civita connection. So they may be the best choice as a good next extension of Levi-Civita connections. Turns out just having skew torsion is still too broad. We need more restrictive conditions and typically some PDE conditions. So the one I'm interested most in today will be closed torsion. So we may want to assume that the torsion tensor itself is closed with respect to the exterior derivative. And that is a good condition, and we'll see examples of that later appearing. But kind of there's a second condition that has been used in the literature, and that's the one I'm going to kind of discuss first, because that's, well, where some more studies have been done so far, and that is the case of parallel torsion. And I'm calling a connection with parallel torsion if the torsion is parallel with respect to the connection itself. So it's kind of this nabla is the connection with torsion T, and then T is parallel with respect to nab. And in this parallel torsion world, one of the arguments why you might want to look at that is they are very nice. I have some nice geometric features. For instance, their curvature would have this pair symmetry like the Levi-Civita does. So they are maybe the nicest type of torsion you can get. So, and in this case, basically the same study as de Rham and Berger have done in the 50s for Levi-Civita has been done for these parallel torsion geometries. But it's been way more recent. So there is a theorem that generalizes de Rham theorem, and the first instance of this has been done by Clayton Moriano Zemmelman, and then we've worked in like a paper with Ilka Agricola and Giulia De Leo on it and extended the theorem. And the version I'm going to present is from a paper I published last year. So suppose we have a parallel torsion geometry, and then we have a reducible holonomy representation. So the tangent space splits as a representation of the holonomy group into two components. One I'm calling V for vertical space and H for horizontal space. And then I want to assume that out of the, well, then I know that the torsion decomposes as well. It is a 3 form, so it has like all these parts, like it has a purely vertical part, it has like 2 mixed parts, and a purely horizontal part. And I want to assume that this one mixed part, the twice vertical, once horizontal part, vanishes. And if I have these two conditions, then I obtain a locally defined Riemannian submersion. So I don't get a product, but I at least get a submersion along the vertical distribution. And basically, I'm projecting it to a horizontal slice. And I can push my geometry also down to this horizontal slice, and then and in the sense that the purely horizontal part of my torsion tensor, so the part that is purely horizontal, is projectable along the submersion. And well, I told you how to get connections with skew torsion. I can, in this way, create a connection with skew torsion on the base. So just add this new projected horizontal torsion to my Levi-Civita connection on the base. And I get a new connection with skew torsion. And it turns out this is very much related to the connection I had on top in this very neat formula here. So if I want to have the covariant derivative on the base, then I just horizontally lift the vector field I'm trying to take the covariant derivative of, and also the vector in the direction I want to take the covariant derivative of. I take the covariant derivative with respect to my connection upstairs, and then I project it back down. And it does not matter to which point I lift it or whatnot. That just doesn't matter. So in that sense, I can consider this connection nabla check on the base as a projection of the connection nabla on the total space. And then there is this very nice property that this connection I've defined has, again, parallel skew torsion. So my base space is, again, a parallel torsion geometry. So in this sense, this theorem allows us to reduce the dimension of a manifold. So basically, we split off the vertical part. We just stay at the horizontal dimension and are left in the same place as before. Two remarks. So I suppose that this part of the torsion, this twice vertical, once horizontal part, that vanishes. And that is actually equivalent to saying that the vertical distribution is integrable, which is, of course, crucial for having submersion. But luckily, that is not a super restrictive condition. In fact, Clayton, Moriano, Zemmelmann, in their seminal paper on this, they showed that if the holonomy is in some way reducible, there's at least some decomposition such that this mixed part vanishes. So we can always apply this theorem in at least one way. It turns out for some manifolds you can apply it in several ways, and there's sometimes decompositions where you cannot apply it, but there's at least some way to apply it.
Sorry, can you give an example of this last thing you mentioned?
I mean, okay, I'm not going to speak, but we applied it to 3 alpha delta Sasaki geometry. And it turns out you have this standard, you get this result, say the 3 Sasaki manifold fibers over a quaternionic Kähler manifold on a base. And that would be one submersion that you can always do, and you can frame it in terms of this theorem. But now if you have like a specific scaling of the fiber and the base, you get like that all the rib vector fields are parallel with respect to this certain connection. And now you can also take a one-dimensional submersion instead. And if you do so, you get to the nearly Kähler structure on the twistor space instead. So you can do either one-dimensional or you do a 3-dimensional submersion and you get like different ones. However, what you cannot do is you cannot do a 2-dimensional submersion, even though that would also be possible as a splitting of the holonomy.
So sorry, it's possible as a splitting of the holonomy, but it doesn't satisfy the TM vanishing.
Exactly. So you because the 3 rib vector fields are just parallel representation of the holonomy. But the only ones that satisfy this condition is like either 1-dimensional or a 3-dimensional distribution.
I see.
Thank you. So yeah, we have this theorem, and the original application of this theorem, as it was intended by Clayton, Moriano, Zemmelmann, was to classify parallel torsion geometries. And basically, what they did is they used the theorem to, reduce dimension until they arrive at some irreducible parallel torsion geometry. And that way you get like a bundle decomposition, and then you just have to classify the irreducible parallel torsion geometries, and that was done like way earlier by Clayton and Swan. So there's a Bezier type theorem. It basically tells you there is a generalization of the symmetric case, namely naturally reductive, and then there's nearly parallel G2 and nearly KLR6 manifolds. And that's all the additional things you get. Apart from that, you just get the Bezier list. So that's kind of the original application of this theorem. But we found other use cases of it. So in fact, and that's the example I just gave, the interest Ilka, Julia, and me had in this kind of theorem was because we were studying 3 alpha delta Sasaki manifolds, and I'm not going to speak about them in this talk, but we can basically show, we can give a structure theorem, these the alpha delta Sasaki manifolds 5 over quaternion Kähler, or bifolds at least. So there's kind of a second use case is a structure theorem, and then we found a third use case, and that is it simplifies differential equations. I'm considering differential equations here in a broader sense. So one of our goals here was to investigate the curvature of these 3 alpha delta Sasaki manifolds, and we were basically able to do that because we figured this fibration over quaternion Kähler manifolds basically decomposes the curvature, and then you have to fiddle around a bit, and then you can show that it, under certain circumstances, you get like strongly positive or strongly non-negative curvature. I don't want to go into details. Basically, you get like complicated curvature formulas, and you can separate them along this submersion. And the same kind of trick is the foundation of a joint paper with Matteo Galdeano. So we worked on this heterotic G2 system, and there are probably several people in the audience who know more about the system than I do. But basically our idea was, can we apply the same thing? Can we apply it to connection or to geometries with reducible parallel torsion holonomies? And we could do that, and it turns out we can then, again, along the submersion, reduce the dimension and get very simple parts that we can explicitly solve. And therefore, we got like a solution to the heterotic G2 system. But back to our original question, we wanted to extend Berger's theorem, or the study of Berger and de Rham, to more interesting geometries, having more possible holonomy groups. And it turns out, well, that's parallel torsion is still kind of restrictive. And that is for a very good reason, namely, you have that the torsion is parallel, so the holonomy has to be inside the stabilizer of the torsion, so it has to be the stabilizer of a 3 form, and there are just so many groups that are stabilizer of a 3 form in a given dimension. So that's also the only reason why this classification scheme of Clayton and Swan was even possible in the first place. Okay, so parallel torsion, very nice work that has been done there, but still too restrictive. So let's go into the closed torsion case. And it turns out we get basically the same theorem as in the parallel torsion. So we have a closed torsion geometry, we have a reducible holonomy representation, and once again, we want to assume that this mixed part vanishes. And then we get basically the same results. So we get the locally defined Riemannian submersion along the vertical distribution. The horizontal part of the torsion is projectable and induces a new connection on the base. And this connection, nabla check, is again the can be considered a projected connection of the one on the total space. Now, the last part was that in the parallel torsion case, this base geometry was again the parallel torsion geometry. So one would hope that maybe the base geometry here is again a closed torsion geometry. Turns out that doesn't really work. Instead, we get this second mixed part of the torsion that restricts our closed torsion on the base. So usually this will not vanish. So there is some cases, namely if both of the mixed torsion parts of our both mixed torsion parts vanish. So not only one that we require to vanish, but also the twice horizontal ones vertical. However, in this case, it turns out that we can apply this theorem kind of with reverse roles of vertical and horizontal part, and it tells us we only or we're left with a product geometry, at least locally.
Sorry, Leander. So in that formula for the right-hand side, I guess I mean there can be a contribution from the like purely horizontal part of T.
No, I mean this
Oh,
up
I see.
here,
Sorry. Yeah.
I'm
Okay.
just considering the vertical part
Yeah, yeah.
of the
Okay. Got it.
metric. So we only have this mixed part appearing here.
Oh, yeah, I see. Thank you.
Yeah. So, but one of the interesting questions I have is like, is there any example where this vanishes even though we are not in a product or local product setting? And I don't know. I don't have examples. So, well, back to the question, is this now more generic? Is this a good generalization of Bézier's theorem? Do we find more geometries? And the first thing seems kind of promising. So closed torsion geometries are easy to find. You take a closed three form, you add your Levi-Civita connection and this closed three form, and there you go. You have a closed torsion connection and a closed torsion geometry. So they're kind of easy to find. Surprisingly, it's hard to cook up good examples. So few interesting examples was known holonomy. I've been running around with this theorem for quite a while and didn't know any examples, and I was like looking for them. And basically, I only found them last year. And there are going to be two types of examples. And the first one is what I call the string background perspective. And this is where Jeff, of course, knows a lot more than me. But basically, there has been a study of these string backgrounds, and it goes back to some physicists. There are lots of dots here, which just is I don't know who. Or there are lots of physicists who worked in this field, and I'm not going to cite all their papers right here. Then I cited now some of the papers I've actually read, and then, well, there are more papers on this. So this is a big story. People have worked a lot in this. And the way I'm going to present it is from this paper by Aaron Kennan and Jeff Streets from last November. But yeah, just saying it is not as simple. It has been a long time in development. So the story goes like this. For suitable geometries, I'm not going to detail what are suitable geometries. If you want to know more about it, ask Jeff or just look in their paper. That's probably the best source to get started with this world. So for suitable geometries, we have a leaf form theta and some kind of potential function f. And it turns out that for generalized Ricci flow reasons, basically we have this, it's a generalized Ricci soliton. And on the one hand side, it has to be with this potential function df here. And for a different reason, it has to be also Ricci soliton with generalized Ricci soliton with respect to the Lie form theta. So it has to satisfy both of these equations, and now you know that if you subtract them, then you see that this form theta minus df is parallel with respect to a connection nabla that appears here. And so we get a parallel vector field in this way, and that implies basically what we want, namely that the holonomy splits. It has at least one trivial representation, and then its orthogonal complement is kind of the remaining representation. So there we have like a playing ground of geometries where we have where we know that, well, I have not mentioned it on the slide, but those are all closed torsion geometries and reducible holonomy. Typical examples out of these kind of suitable geometries is Bismuth-Hermite Einstein. And there we have two parallel vector fields because you get like a connection that parallelizes also complex structure. So we have two parallel directions, and we get a codimension 2 submersion if we consider both of them the vertical part. Similar in the strong hyperkähler torsion, and for all those who do not know what BHE and strong hyperkähler torsion, that's going to be explained on the next slide, so don't worry. And there, by a result of Beatrice Brienza, Fino, Granschaft, and Verbitsky, they show that, well, basically there are 4 parallel vector fields, and what they show is that this distribution is integrable in dimension 8. And I told you that's kind of the second condition I need to apply my submersion theorem. Both of these examples are can be explained using the theorem I've gave before, but in both cases, and for all these string background cases, the results of the theorem have been known. In fact, Aaron and Jeff have a similar kind of theorem in this setup in their paper. So these are not new results. It shows that they're part of a kind of bigger story. So let me remind you kind of what is the main geometry we're talking about here in both the BHE and the strong hyperkähler torsion geometry. So my focus will be on strong Kähler torsion geometries, and which is not Kähler, but it has torsion. So that's kind of, the Kähler is confusing here. It's a generalization of Kähler, but it is a connection with torsion, and the strong refers to it being having closed torsion. So suppose we have a Hermitian manifold. It turns out that in this case, you always have a unique Hermitian connection with Q-symmetric torsion. And you can, well, just write down the torsion, and it's 1/2 this twisted differential of the fundamental form of your Hermitian manifold. And this was done originally by Bismuth, and in the physics world, it's kind of simultaneously been developed by Strominger, so some people call it Strominger connection. I will stick with the usual convention in math, with the Bismuth connection. Now, this is only a connection with Q-symmetric torsion, but we want something with closed torsion, so we call Hermitian manifold strong Kähler torsion if this torsion dc omega is closed, so ddc omega is 0. In many instances, kind of in a study of Hermitian geometry, of complex geometry, people will often call this pluriclosed because of this condition. But since we're focusing on the torsion, I'm sticking with the notion of strong Kähler torsion. It's additionally called Bismuth-Hermite Einstein if this Ricci form, Bismuth-Ricci form, vanishes. So it mimics kind of the Ricci form in classical Kähler geometry. And it turns out that if this vanishes, then in fact, it's what is called not only strong Kähler-Weiss torsion, but kind of a strong Calabi-Yau-Weiss torsion geometry. And finally, a strong hyperkähler-Weiss torsion geometry is basically defining a set of three anti-commuting SKT structures, similar, kind of the full analogy to the Kähler versus hyperkähler case. And now, because we want strong Kähler-Weiss torsion and we have this Bismuth connection, we need to assume that for an SHKT manifold, all the Bismuth connections agree. So this is kind of the full generalization of Kähler, Calabi-Yau, and hyperkähler. Okay, so now that we kind of know the story, we want to understand more, like if we have a submersion due to this closed torsion submersion theorem by reducible holonomy, then we want to say more about the geometry on the base. We have seen that there is at least a connection, so there is some kind of projected geometry on the base, but how does it look precisely? So suppose we have kind of the setup as before, and this is slightly more general. It also applies to the parallel torsion geometry case, the way it's phrased, but basically we have a Riemannian submersion or locally Riemannian submersion, and these kind of connection that where one projects to the other, and then we want to understand the holonomy of the base, and it turns out in one specific instance we can do that. So suppose that the holonomy is inside the stabilizer of some tensor. So we've seen that this is the usual setup we have. In Berger's theorem, for example, we have some kind of tensor. We know that is preserved, so the holonomy is in the stabilizer of this tensor. So if that is the case, and this tensor projects under the submersion, then it turns out that the holonomy of this projected connection on the base, it preserves again the projected omega. So we know that the holonomy is inside the stabilizer of this omega check, which is just a notion I have for the projected tensor. So in the specific case of an SKT manifold and a submersion in SKT geometry, if we assume that the horizontal part is J invariant, and for any vertical vector field, if we plug it into the torsion, this is a 1-1 form, then it turns out that our complex structure projects from our SKT manifold M to this base N. And if it projects, well, we can immediately check that it's again, a complex structure with the setup, and the connection, and this is basically implication of the theorem before, has to preserve this projected J. So it has to be, again, a Hermitian connection on the base. And because, well, we know that the complex structure on the base is integrable, this has to be, again, the Bismuth connection on the base. Let's look at the two examples I mentioned before. So consider the Bismuth-Hermite-Einstein case. And from this long study, we have this vector field V, which is Bismuth parallel. And because the Bismuth connection is a Hermitian connection, also JV is a second parallel vector field. So that implies that the holonomy is inside kind of, well, we have two trivial representations, and the rest of it is an SUN-1. Note the because it's Bismuth-Hermite-Einstein, the holonomy of the Bismuth connection has to be in SUN. Now, in this case, and I should mention, as long as it's not Kähler, these are non-trivial. So we have, in fact, that the holonomy reduces to holonomy inside SUN minus 1 times two trivial representations. And that's, of course, yeah, SUN minus 1 is in UN, which would just be the stabilizer of J. More precisely, the stabilizer of J and the metric G, of course. Well, people and in this story, this is kind of part of all these proofs. If you have in this Bismuth-Hermite-Einstein, you can also check that the complex structure is preserved along these vector fields V and JV. So this is good because this means that our complex structure J projects. And we have just seen that implies that on our base, we again get a complex, well, we have an integrable complex structure J check. And the holonomy of the connection on the base is inside the stabilizer of J check. So this is again in UN minus 1. Note here, from the get-go, you might want to assume that it's again in SUN minus 1. But I mean, I at least have not seen any argument that it should be, and I don't think it is. And if you want to use it, use this theorem to prove so, you would have to show that the complex volume form is also projectable. And well, I don't think this is in general true. At least I've not seen any proof that it is. If someone knows of any such thing, let me know. Okay, let's go to the second example where we basically see the similar story. So suppose we have a strong hyperkähler torsion geometry. Then it turns out we have this unique hyperemission connection. So it preserves all of the complex structures I1, I2, I3, and the metric. So because it also preserves, and then the setup as before applies, so it preserves one vector field V. And then because it's hyperemission, it preserves also the three vector fields I1, V, I2, V, I3. And this implies that the holonomy is, of course, in SPN. And because they are parallel, it's actually in SPN minus 1 and has 4 trivial representations. And now we again would like to have this distribution spanned by V, I1, V, I2, V, I3, V to be integrable, so that we can apply the theorem. Turns out that is not, I mean, there's no general proof. And I've spoke to some people here about it, but basically we have to assume something. So I want to assume this thing, which is called conical in some sense. So the complex structures are all preserved under this vector field V, and the vector fields I1, V, I2, V, and so on, they kind of rotate the complex structure. So IIV rotates IJV to IKV, and IJ to IK. Sorry. And this is actually the setup for n equals 2, so for dimension 8, that is what Brienza, Fino, Ganchaev, and Verbitsky prove in their paper. And it turns out if you have the setup, then the distribution is integrable. It's a bit more than just integrability, but that is at least a consequence. So because we have integrability, we know that the theorem applies, so there has to be a locally defined Riemannian subversion of codimension 4. And then you check, well, these complex structures I clearly are not individually projectable. This equation tells you you cannot project them individually. So you have to be a bit more clever. And what you can figure out, basically, if you've seen these kind of geometries, you see that you can define this four form, which is just the sum of the wedge of the squares of the fundamental forms. And this kind of condition tells you precisely this form omega will be preserved under my vector fields. So this will be preserved under the submersion. So that tells us the holonomy of the connection on the base has to be inside the stabilizer of the projected omega, and this is a quaternionic form. So my holonomy has to live on the base, has to live inside SPn minus 1 times SP1. And once again, this is kind of a step back because we have noted up here that the holonomy is in SPn minus 1, and now the holonomy group has kind of increased. But it's still kind of a special holonomy group and more restrictive holonomy group, so we can project some of the geometry to the base. Okay, are there questions for these examples? Because next slide, I'm going to look into a different class of examples. Okay. Because basically this, I told you this string background perspective is kind of, I learned about it only last year. So I was looking for other kind of examples, and I found a different class of examples as well. And that is in the homogeneous world. So we want to consider homogeneous strong Kähler-Lewis torsion geometries. And for that, they are known to exist on compact semisimple Lie groups of even rank. So they are so-called Samuelson complex structures. So we take a compact semisimple Lie group and we consider its root space decomposition, so Cartan subalgebra, and you split up into its root pairs. And then I've also, for notation reasons, I also split it up into its simple factors. And now we define a Samuelson complex structure by basically defining a complex structure on the complexification of the Lie algebra. So we just have to define it on the root space. And the way you do it is you define it on the roots by just saying for the positive roots, you set it plus I. On the negative roots, you set it minus I. So you only need to worry about what it's on the what J should be on the Cartan subalgebra, and you take any complex structure there. This is an even dimensional vector space, so there is some choice of complex structure. And it turns out like this all work by Samuelson, these are integrable complex structures. And well, basically they are they're unique given by the choice of this JT up to some finite orbit of holomorphic automorphisms. But we're not only caring for complex manifolds, we want to have Hermitian manifolds, so we want to define Hermitian metrics. And for that reason, I'm kind of giving the most general Hermitian metric you would assume. So basically, I take the Killing form and I'm scaling it. And the way I'm scaling it is basically by some factor C alpha. So these pair have to be scaled in the same way because they are the ones that are preserved on a J. So you cannot scale, you cannot have like different factors on these. And then you just fix the scaling of of the maximal torus. And then because if you have J in a way where it mixes the simple parts, you might have to include these or fix these parameters lambda I in a precise way. There is at least like if it is complex irreducible, there's exactly one way of fixing the lambda I, so that is Hermitian. If it's complex reducible, so you have like several complex factors, you can you have some choice in the lambda i's. But for the rest of it, we won't really care about lambda i's. The important part is we have this C alphas that we can scale as we like, so as long as they're positive, of course. And then Jorge and Montedoro, they basically gave a classification of strong Kähler-Lewis torsion on these semi-simple Lie groups, on these Samuelson spaces, and they showed these kind of Hermitian metrics are SKT if and only if these C alpha, these scaling factors here, satisfy that C alpha plus beta is C alpha plus C beta, so they are almost additive, but there's like a -1. So you can basically just add them up, and then that's the way you get a SKT structure. And conversely, so these are by default left and T bi-invariant. And what Lorette and Montedoro show is that, in fact, any left and T invariant SKT structure on a compact semi-simple group is given in this way. So with this complex structure and this Hermitian metric. Okay, so now we have the setup. How do we obtain such G? So how do we get these coefficients in a way that they satisfy this condition? And Lorette and Montedoro also answer this question. It's kind of simple and instructive. So you start by your set of simple roots, and you set the coefficients for these simple roots arbitrary. There is a bit of caveat. You need to check that in the end your metric will be positive definite. But if you set them big enough, then that's not a problem. So you start with your simple roots, and then you know all your roots can be expressed as the sum of these simple roots. So you can decompose them, and this condition tells you then exactly how these coefficients for any root alpha has to be, how to define this C alpha, and it's just in this way. So we basically, the only choice we have is by fixing the C alpha on the simple roots. One specific case I should mention, if for any set of simple roots, my coefficient is 1, then it turns out all these sums here are 1. So if my root is just a sum of these simple roots where the coefficients are 1, then C alpha for this root will be again 1 because all of these parts vanish. So we kind of get these subroot systems where the coefficients are all 1. Note if I fix like all of them 1, or just the simple roots 1, and then therefore I get all of my C alphas to be 1, then this is exactly the case if the metric G is bi-invariant. And it turns out bi-invariant Samuelson Hermitian structures are known to be Bismuth flat. But that doesn't generalize. So in general, Samuelson SKT spaces are not Bismuth flat. They're not even a Bismuth Hermite Einstein. Okay, But what about their holonomy? That's what we're interested in. Is it maybe reducible? And well, I wouldn't probably wouldn't talk about them here if they were not. So it turns out the first thing, you don't even need the SKT condition. It turns out if you have a Samuelson Hermitian structure um, in this form as above, then it turns out that the Cartan subalgebra, or the maximal torus, is a trivial representation for the Bismuth holonomy. So this does not even require you to be SKT. But in the SKT case, we can do more. So I told you before, kind of these or these simple roots where the coefficients are 1 are kind of special. And I'm going to call them Imax. And then I can show that the holonomy decomposes, so the trivial representation of the maxima torus, and then all the roots that are generated by these simple roots, which are 1, they all split off as their real root spaces, so as two-dimensional representations of the holonomy. And then kind of the rest of them are just grouped into for the component. So we have kind of trivial representation, two-dimensional representations, and the rest. Okay, so we have a splitting holonomy. We want to apply the closed torsion submersion theorem. And it turns out we can do just that. So suppose you have any set of simple roots that are inside this Imax, so their coefficients are 1, so that they split off, then we can consider the subalgebra, which takes the maximal torus, and it takes all these root spaces generalized by I. That is a subalgebra, so it integrates to a subgroup of G. And, well, you get from the submersion theorem that there is a remaining submersion from G to G mod HI. And it turns out by the arguments we had before, you have to check, of course, that the conditions are satisfied, that on the base you again get a complex structure, and the connection on G, the Bismuth connection on G, projects to the Bismuth connection on this G mod HI. Now these G mod HI are exactly the generalized Flack manifolds. However, when we talk about generalized Flack manifolds, what you usually think of is the metric induced from the bi-invariant metric. That would be a Kähler metric. But here we still have some of these scalings preserved. So these might be generalized Flack manifolds, but with not the Kähler metric. Yeah. So kind of these results are not new, that there exist these Hermitian submersions, but it's kind of interesting that they once again are introduced by reducible holonomy. Yeah, and I think that's all I have, all I wanted to say. So thank you for having me.
Okay, yeah, thanks, Leander. Are there any questions? I guess about this last point, right, you said these Gmod HI will typically be Kähler manifolds, but somehow the induced, at least in like the cases that I think I can fit into your corollary, somehow the induced geometry, I mean, it solves this sort of Hallstrominger system, really. Like you have this.
I mean, they would be Kähler if we start with the bi-invariant metric here. So if all the C alphas are 1, then we can still apply the theorem because we know that, well, everything splits off. Like this, like the entire root system will be here, so it will split off into all these two-dimensional representations. And then we can apply this for all the DHI, and you get to the calorimetric on the base.
Oh,
If that
yes.
is not, then you don't like you project from a non-biinvariant metric. You start with some C alpha non-1. Well, you get to a different metric, and that is not Kähler anymore.
Okay. I think I understand. Yeah, you're just reducing like general left invariant SKT here.
Yes.
Yeah, I see. Okay. Okay. Um, okay. Any others? Um, okay. Well, yeah, if not, let's thank Leander again for the very nice talk.